Cassini spent its final 20 minutes inside Saturn's atmosphere fighting to stay alive. It was the morning of September 15th, 2017. The spacecraft was falling toward the cloud tops of a planet it had circled for 13 years. NASA had already made a hard decision. Cassini would take no pictures during this final plunge. Every measure of its power went to live science instead. Consider 3 facts about that last morning. Cassini's small thrusters were built for gentle nudges in the vacuum of space. In the final seconds, they fired at 100% of their strength. They had never been driven that hard before. The radio signal that confirmed the spacecraft's death did not reach Earth for another 83 minutes. By the time engineers heard it end, Cassini had already been gone for over an hour, and the deepest measurements ever taken inside Saturn came from an instrument tasting the atmosphere as the spacecraft came apart. The problem facing the engineers was brutal in its simplicity. How do you keep a machine transmitting while a planet tears it apart? Cassini had to hold one antenna aimed at Earth. The thickening atmosphere pushed against the spacecraft like a rising wind. The thrusters had to win that fight long enough to send the data home. Every second of pointing was another second of discovery. Every second lost was silence. This episode follows Cassini through its last dive between Saturn and its rings. It follows the losing battle of those thrusters against the drag. It follows the final stream of data that crossed the solar system before the signal died. And it asks why NASA chose to destroy a working spacecraft on purpose. If you would like more long-form space journeys like this one, consider subscribing to Gravity of Sleep. Now we return to the story. Cassini's ending did not begin on that September morning. It began years earlier, in the quiet arithmetic of orbits and fuel. The spacecraft was running low on the propellant that let it steer. Without steering, it could not point its antenna or aim its cameras. A drifting probe with empty tanks is simply a piece of debris, and Saturn is a world with dangerous neighbors. So the people who ran the mission decided how it would end while it was still healthy. They would fly it into the planet itself. To understand that choice, it helps to remember how far this machine had already traveled. Cassini launched from Cape Canaveral on October 15, 1997. A powerful Titan rocket carried it away from Earth. It crossed the inner solar system for nearly 7 years. On July 1, 2004, it slipped into orbit around Saturn. No spacecraft had ever orbited that planet before. It carried a small European lander named Huygens. In January of 2005, Huygens descended through the haze of Titan and touched the surface. That was the first landing on a moon in the outer solar system. For 13 years after arrival, Cassini circled Saturn again and again. It mapped storms and studied the rings from many angles. It flew close to moons no one had ever seen in detail. But fuel is finite, and every maneuver spent a little more. By early 2017, the mission had entered its last chapter. The team gave that chapter a name. They called it the Grand Finale. The Grand Finale was not a slow drift toward the end. It was a bold new set of orbits, unlike anything Cassini had flown before. 22 times, the spacecraft dove through a narrow gap between Saturn and its innermost ring. That gap is about 1,200 miles wide. In the scale of a planet, that is a thin corridor. On one side stood the top of Saturn's atmosphere. On the other side hung a wall of orbiting ice and rock. Cassini threaded that gap over and over across roughly 5 months. The first of those dives came on April 26, 2017. It was set up a few days before by a close pass of Titan. On April 22nd, Cassini swung past that giant moon one more time. Titan's gravity acted like a hand on the spacecraft's course. That single flyby changed Cassini's velocity by about 1,800 miles per hour. That was enough to bend its path into the gap. From then on, each loop carried it between the planet and the rings. Its height above the cloud tops changed from pass to pass. It ranged from about 1,000 miles to about 2,500 miles. Those orbits were a scientist's dream and an engineer's worry at once. No spacecraft had ever flown so close to Saturn. The gap had never been crossed by a human machine. There was a real chance that a stray ring particle could strike the probe. So on the first crossings, Cassini turned its large dish antenna forward like a shield. The team held their breath and waited for the signal. The spacecraft came through. The gap, it turned out, was remarkably clean, and each pass gathered measurements no instrument had ever made from that distance. The grand finale was designed to end in the planet. April of 2017 was when the spacecraft was committed to that final impact course. From that point, the mathematics of the mission pointed in one direction. Every remaining orbit brought Cassini a little closer to the day it would fall. The team knew the exact morning. They knew it would be September 15th, and they built the entire last stretch of the mission around a single goal. They wanted to keep the spacecraft alive and talking for as long as physics would allow. Before the plunge, Cassini said goodbye to the moon that had shaped its whole journey. On September 11th, 2017, it made a distant final flyby of Titan. The team called it the goodbye kiss. Cassini passed roughly 74,000 miles from the moon. That was not close by the standards of its many earlier visits. But it did not need to be close. It needed one last gravitational nudge. Titan's pull bent the spacecraft's orbit just enough. That bend lowered the low point of the next loop into Saturn's atmosphere. After that pass, atmospheric entry was guaranteed. There was no maneuver left that could pull Cassini back out. Then came the last pictures. Cassini took its final camera images on September 14th. The shutter closed for the last time at 8 minutes past 3 in the afternoon, Eastern Time. The spacecraft looked back at the worlds it had come to know. It photographed hazy Titan and the bright, icy Enceladus. It captured a tiny object in the rings that scientists had nicknamed Peggy. It caught a feature in the rings shaped by a hidden moonlet, a kind of gap called a propeller, and it made a final color view of Saturn, its rings, and the glowing aurora over the North Pole. Those were the last images this spacecraft would ever send. After the pictures were taken, Cassini turned itself toward home. At 22 minutes past 4 that afternoon, it swung its antenna to point at Earth. From that moment, the mission's purpose narrowed to a single thread: keep that antenna aimed, keep the data flowing. Whatever the spacecraft learned in its last hours had to be sent immediately, because nothing would survive to be sent later. Here is why there would be no images during the plunge itself. Pictures are large. They take up a great deal of room in a radio transmission. Sending them would have crowded out other measurements, and in the final hours, the team wanted something pictures could not give them. They wanted real-time readings of the atmosphere and the fields around the planet. Particle counts, magnetic readings, the chemistry of the gas itself. So the engineers made the trade on purpose. They gave up the last photographs to make room for the last science. The plunge would be recorded in numbers, not in images. That choice tells you something about how this ending was planned. It was not a crash that scientists simply watched. It was an experiment they designed. Saturn's upper atmosphere had never been sampled from the inside. No probe had ever flown into it and reported back in the moment. Cassini's final fall was the only chance to do that, so the spacecraft was aimed like a needle into the top of the planet, and its instruments were set to drink in everything they could on the way down. The last full day of the mission moved on a strict clock. Early in the morning of September 15th, Cassini crossed a familiar boundary one final time. At 8 minutes past 1 in the morning, Eastern Time, it passed the distance of Enceladus's orbit. It would never cross that line again. Enceladus was one of the great discoveries of the mission. It was also one of the reasons Cassini was about to be destroyed. We will come back to that. A little more than 2 hours later, the spacecraft made a careful adjustment. At 14 minutes past 3 in the morning, Cassini began a slow roll. The turn took about 5 minutes. Its purpose was to bring one particular instrument to the front. That instrument was the ion and neutral mass spectrometer. Its job was to identify the gases it flew through. By rolling, Cassini pointed it straight along the direction of travel. It would meet Saturn's atmosphere head-on. Every molecule the spacecraft struck would flow directly into its intake. For the first time, a machine would measure Saturn's air by being inside it. With that role complete, everything was in place. The cameras were already dark. The antenna was locked on Earth. The mass spectrometer faced forward into the oncoming gas. The thrusters stood ready to fight whatever the atmosphere would bring, and far above the cloud tops, Cassini fell toward the moment it was built in these final months to meet. The atmosphere was still minutes away, but the spacecraft was already committed, already falling, already counting down toward its first touch of a planet it had studied from a distance for 13 years. For more than 3 hours, Cassini simply fell. Nothing dramatic happened in that long stretch. The spacecraft coasted along a curve set weeks before. Saturn grew slowly across a view no camera was watching. The mass spectrometer waited with its intake open to the dark. The antenna held its lock on a pale point of light. That point was Earth, more than 1 billion kilometers behind it. Every system that could still report was reporting, and the planet ahead kept pulling harder with each passing minute. Saturn's gravity did to Cassini what it does to everything that falls. It added speed. By the time the outer atmosphere was near, the spacecraft was moving at a staggering rate. It approached the cloud tops at roughly 70,000 miles an hour. Some measurements place that speed closer to 77,000. Either figure is difficult to hold in the mind. At that velocity, a machine crosses the width of a country in minutes. Cassini was about to cross into a planet. The point of entry had been chosen with care. Cassini would meet Saturn on the day side, near local noon. Its target sat around 10 degrees north of the equator. Sunlight would fall on the clouds it was diving toward. This mattered for the science. An atmosphere lit by the sun reveals more than one hidden in shadow. It also meant the last place Cassini touched was a bright band of Saturn's northern hemisphere. No one would ever see it. But the geometry was known to the second. Entry began around 31 minutes past 6 in the morning, Eastern Time. At that instant, Cassini was still roughly 1,200 miles above the clouds. That sounds like a wide margin. It was not. Saturn's atmosphere does not end at a surface. It thins upward for hundreds of miles into near vacuum. Cassini was already inside the faint outer edge of the planet. The gas there was almost nothing. Almost nothing, at 70,000 miles an hour, is still a wall. The first effect was gentle. A trace of atmosphere began to push against the spacecraft. That push tried to turn Cassini, to tip its antenna away from Earth. The spacecraft answered at once. Its small thrusters began to fire. At first they worked at only about 10% of their capacity. That was enough. 1/10 of their strength held the antenna steady against the earliest drag. For a short time, the machine and the planet were nearly matched. Cassini kept talking. The data kept flowing home. These thrusters were never built for this. They burned hydrazine, a simple rocket fuel. Each one produced about half a newton of force. Half a newton is a small thing. On Earth it is roughly the weight of a tennis ball resting in your hand. That was the entire force each thruster could bring to the fight. Cassini carried several of them. Together they had guided the spacecraft for 20 years with tiny, precise nudges. Now those same gentle nudges were all that stood between order and tumbling. Holding an antenna on a target across 1 billion kilometers demands astonishing precision. In the final hour, Cassini managed this through a method the engineers called bang-bang control. The spacecraft did not hold perfectly still. It rocked back and forth by the smallest amounts. It swung through roughly 2 milliradians, about 1/10 of a single degree. Every few minutes, a thruster pulsed to correct the drift. Then it drifted the other way, and another pulse answered. Julie Webster, who managed spacecraft operations, described it plainly. The probe was rocking and pulsing, over and over, to keep its beam aimed at home. For a while, this careful rhythm was enough, but Cassini was falling deeper every second, and the atmosphere below grew thicker with every mile. The gentle push became a hard shove. 10% of thruster power no longer held the line. So the spacecraft asked for more. It ramped its thrusters upward, quickly. In about 1 minute, the firing climbed from 10% to nearly 100%. The half-Newton engines went from a whisper to a strain. They were doing everything they were capable of doing. Think of what that means. A set of thrusters designed to sip fuel and turn a spacecraft slowly was now firing almost flat out. Each still produced only the force of a tennis ball's weight. Against them pressed the outer atmosphere of a planet 9 times wider than Earth. The mismatch was total, but the thrusters were not trying to stop Cassini. They could never stop it. They were only trying to keep it pointed the right way for a few more seconds. And for a few more seconds, they succeeded. There is a detail here worth pausing on. The density of gas Cassini was fighting was extraordinarily thin. It was comparable to the tenuous gas found where the International Space Station orbits Earth. Astronauts live in that near vacuum, without feeling any wind at all. At the station's altitude, that whisper of atmosphere is so faint it takes years to drag a spacecraft down. Yet it was tearing at Cassini almost instantly. The difference was speed. Cassini was moving about 4.5 times faster than the space station. At that velocity, the faintest gas becomes a hard force. This is why the final minutes were a battle and not a slow decline. The atmosphere did not have to be dense. It only had to be there, met at enormous speed. Every mile Cassini fell, the gas grew a little thicker. Every increase in thickness meant a stronger twist on the spacecraft. And the thrusters had already reached their limit. Once they hit 100%, there was nothing left to give. From that point, the outcome was fixed. The only question was how long the machine could hold its aim. The answer, remarkably, was 91 seconds. From the moment Cassini first met measurable drag, it held its orientation and kept transmitting for 1.5 minutes. 91 seconds does not sound like a triumph. It was won. The spacecraft was never designed to enter an atmosphere. It had no heat shield. It had no aerodynamic shape. It was a bus-sized collection of antennas, booms and instruments, built for the emptiness of space. And that fragile, ungainly machine flew into a planet and kept talking for 91 seconds. Every one of those seconds carried new measurements toward Earth. Those measurements were the entire reason for the choreography. The mass spectrometer, pointed forward through the whole descent, was drinking the atmosphere directly. For the first time in history, an instrument was tasting Saturn's air from inside it. It counted the molecules streaming into its intake. It reported what Saturn's upper atmosphere is actually made of. Not from a distance, but by touch. Every second the antenna held, that composition data reached the ground. To understand why this mattered, consider how planets are usually studied. For most of Cassini's mission, Saturn's atmosphere was read from afar. Light passing through the gas was measured. Colors were split apart to guess at chemistry. These methods are powerful, but they are always indirect. They infer the air rather than handle it. In its final minutes, Cassini stopped inferring. It flew its sensor into the gas and let the planet pour through it. There is no substitute for that. A single direct sample can settle questions that remote observation only circles. Around Cassini, the rest of the spacecraft kept working too. This was not a single instrument's moment. Many of the science tools remained on and reporting through the plunge. Magnetic sensors read the field. Plasma instruments counted charged particles. Radio science listened to the way Cassini's own signal bent through the gas. Together they were building the deepest direct portrait ever made of Saturn's outer layers. The spacecraft was dying and studying at the same time. It spent its last working minute doing exactly the work it was sent to do. On Earth, none of this arrived as a picture. There was no dramatic image of clouds rushing up. There was only a stream of numbers on screens in a quiet control room. Engineers and scientists watched the signal hold, then watched the data climb in. Each new value was something no one had ever recorded. A room full of people sat still and let a spacecraft more than 1 billion kilometers away hand them the composition of a planet. And still the thrusters fought. In the final stretch, their firing was no longer a rhythm of separate pulses. It became almost continuous. In roughly the last 20 seconds, the thrusters burned at full capacity without pause. There was no more back and forth, no gentle rocking. There was only a steady, maximum effort to hold the antenna on Earth for as long as physically possible. The half-Newton engines were wide open, pressing against a planet, buying time by the second. It was a losing fight conducted with complete commitment. Somewhere in that final push, the balance tipped. The atmosphere thickened past the point the thrusters could answer. The force on the spacecraft exceeded the force it could produce. Slowly at first, and then not so slowly, Cassini began to lose the argument. Its careful aim started to slip. The beam that had held Earth for 20 years began, at last, to wander off the mark. The machine was still alive, it was still transmitting, but the narrow pathway of its signal was starting to drift away from the small blue point it had been speaking to. The last measurements were still leaving the spacecraft. The question now was only how many of them would find their way home. For most of that final minute, the machine kept its promise. It had encountered measurable drag, and it did not surrender. It held its orientation and kept transmitting for 91 seconds. That number is small when written down. It was enormous inside the spacecraft. 91 seconds is the length of time a falling probe fought a planet, and still spoke clearly to a world nearly 1 billion miles behind it. The density it pushed through was thin. It was comparable to the tenuous gas found at the altitude where the International Space Station circles the Earth. But Cassini was not drifting through that gas. It was tearing through it about 4.5 times faster than the station moves. At that speed, even a whisper of atmosphere becomes a wall. So the drift that began was not a failure of will. It was arithmetic. The thrusters had reached their ceiling. The planet had not reached its. Once the two forces crossed, the outcome was decided, and only the timing remained uncertain. Cassini began to tip. In its final 8 seconds, the spacecraft slowly rolled backward. The motion was gentle by the standards of a machine falling into Saturn. It was fatal by the standards of a radio link. The high-gain antenna, which had pointed at Earth through 20 years of travel, began to swing away from the small target it had always found. When an antenna turns off its mark, the information goes first. The rich stream of science and engineering telemetry, the numbers describing temperature and density and field strength, depends on a strong and steady lock. That lock broke. The data vanished. What remained was thinner and simpler. A bare radio carrier survived. A carrier is the underlying tone of a transmission, with nothing riding on it. It carries no measurements and no words. It only says that a transmitter is still switched on and still aimed close enough to be heard. That empty tone persisted for about 24 more seconds after the data had already gone. For those final seconds, the spacecraft was still calling, but it had nothing left to report except its own continued existence. Then, even that faded. The carrier weakened as the antenna wandered further, and the tone that had crossed the solar system slid down toward the noise. On the screens where engineers watched the signal, there was a moment that looked almost like hope. The line, which had been sinking, briefly lifted again. To an eye desperate for good news, it looked as though the spacecraft had steadied itself. It looked like a recovery. It was not. Engineers later determined that the brief return was not Cassini righting its aim. It was a side lobe of the antenna's beam pattern, sweeping across the Earth as the spacecraft tumbled. Every dish radiates a main beam and smaller beams to the side, like faint echoes of the central one. As Cassini rolled, one of those smaller beams happened to cross our planet. The signal flickered up not because the machine had saved itself, but because it was turning, and a weaker part of its voice passed over us on the way down. It was the last accident of geometry in a mission built on precision. After that, the tone did not return. The line settled into the flat, featureless hiss that fills every radio receiver pointed at the sky. It is the sound of a universe with nothing to say. The spacecraft was gone. And here the strangest fact of the entire ending asserts itself, quietly and without mercy. The people watching those screens were not watching Cassini die, they were watching a memory arrive. Saturn was then about 932 million miles from Earth. That is roughly 1.5 billion kilometers of empty space between the falling probe and the antennas listening for it. Radio waves are fast. They move at the speed of light, the fastest anything can travel. Even so, across that gulf, the fastest thing in nature needs time. A signal leaving Saturn took about 83 minutes to reach the receivers on Earth. 83 minutes. Nearly an hour and a half. So every tremor in that final signal, every drop and flicker and the false lift of the side lobe, had happened long before anyone saw it. The plunge, the burn, the tip, the silence, all of it was already finished. Cassini had already been destroyed for 83 minutes by the time its last faint carrier was detected, and the mission was declared over. The engineers were reading a letter from a spacecraft that no longer existed. They were hearing the past. The man who led the mission understood this in advance. Before the encounter, Cassini's program manager, Earl Mays, described the coming silence in a way that has stayed with many who heard it. He said the spacecraft's final signal would be like an echo. He said it would radiate across the solar system for nearly an hour and a half after Cassini itself had gone. That is not poetry stretched over a technical fact. It is the technical fact, stated plainly. The signal outlived its source. For 83 minutes, a voice travelled through the dark from a machine that had already burned. When the voice finally arrived, the thing that made it was scattered vapor in an alien sky. The place that caught that echo sat on the far side of our own planet. During those hours, Saturn hung in the skies over the southern hemisphere, so the listening fell to the Deep Space Network's great station near Canberra, in Australia. There, a dish 230 feet across, one of the largest steerable antennas ever built, was turned toward the ringed world and held fixed. Such an antenna can hear a transmitter fainter than almost anything else humans have made to listen with. It had to be. By the end, Cassini's radio power was modest, and its distance was immense, and the tone it sent was thinner than a whisper folded into the roar of space. The Canberra dish gathered that thread of signal, and the moment it fell away for good was marked exactly. Loss of signal was confirmed at 4 seconds short of 7:56 that morning, Eastern Time in the United States. In the more universal clock that scientists keep, it was just before noon in Coordinated Time. On the ground in Australia, it was already the middle of the afternoon. A single instant, recorded to the second, for an event that had truly occurred 83 minutes earlier and nearly 1 billion miles away. This is the honest shape of what Cassini recorded in its final 20 minutes inside Saturn. Not a photograph, not a scream, a steady, disciplined stream of measurement, followed by a fading tone, followed by a silence that reached us late. The record is not dramatic in the way films are dramatic. It is more unsettling than that. It is a machine describing its own end in real time, calmly, until the description stopped, and then the plainer fact of its persistence, until that stopped too. It is worth being precise about what was and was not captured, because the difference matters. There were no images from the plunge itself. That was a deliberate choice, not a failure. Sending pictures would have consumed the narrow data rate that Cassini had left, and the mission wanted every available bit for measurements that could be made only once and never again. So the cameras had already fallen silent the day before. What flowed home in those final minutes instead was invisible to the eye, but priceless to science. 8 of the spacecraft's 12 instruments were switched on and working as it fell. Chief among them was a device built to taste the air. Its full name is the Ion and Neutral Mass Spectrometer, and its task is to sort the atoms and molecules of a gas and count them by their mass. In those last minutes, it was pointed directly into the oncoming flow, drinking the upper atmosphere of Saturn as the spacecraft rammed into it. For the first time in history, a machine was sampling the gas of that planet directly, from the inside, rather than guessing at it from a distance. Alongside it, instruments measured the magnetic field, the charged particles, and the faint radio environment of a place no probe had ever reached. Because of that final dive, Cassini made the deepest direct measurements ever taken of Saturn's atmosphere and its surrounding space. The deepest reading of the plasma around the planet, the deepest reading of the magnetic field, the deepest reading of temperature and composition. And it sent those readings home in near real time, up to the very second its antenna could no longer hold Earth. The spacecraft was not merely dying for the sake of a clean ending. It was working. It turned its own destruction into an experiment that could be run in no other way. To learn what the top of Saturn's atmosphere is truly made of, something had to go there and be consumed by it. Cassini volunteered to be the instrument and the sample at once. This is a rare thing in exploration. Most missions end when a spacecraft fails, or runs out of fuel, or simply falls silent from age and distance, its final moment unwitnessed and unplanned. Cassini's end was authored. Every second of that plunge had a purpose assigned to it long before the plunge began. The roll that pointed the spectrometer forward, the thrusters ordered to fight for the antenna, the instruments chosen to stay awake, the data prioritized over the pictures. None of it was accident. A team of people decided, years earlier, exactly how their spacecraft would die, and then they built the commands that carried out that decision on a morning when the spacecraft was too far away to be helped and far too far away to be saved. To understand why they made that choice, and why they were willing to burn a working machine that still had years of life in it, we have to go back from the fire to the reason for the fire. The story of that morning begins with a launch. Cassini left Earth on the 15th of October, 1997. It rode a Titan 4B Centaur rocket up from Cape Canaveral in Florida. The spacecraft that would one day fall into Saturn was, at that moment, only beginning a journey of nearly 7 years. It did not fly straight there. No rocket then built could carry so heavy a machine directly to the outer solar system. So Cassini borrowed speed from other worlds. It swung past Venus twice. It passed Earth once more. It flew by Jupiter and gathered momentum from the giant planet's gravity. Each pass added velocity that no engine on board could have supplied. The long detour was not a delay. It was the only way to reach Saturn at all. Cassini arrived on the 1st of July, 2004. It fired its main engine and slipped into orbit around Saturn. No spacecraft had ever done this before. Cassini became the first machine from Earth to circle the ringed planet. For the next 13 years it would remain there. It traced loop after loop around a world no probe had ever studied from close range. And it did not travel alone. It carried a passenger for part of that journey. The passenger was a small probe named Huygens, built by the European Space Agency. Huygens rode with Cassini all the way from Earth. Late in 2004, Cassini released it toward Titan, the largest of Saturn's moons. Huygens fell through Titan's thick orange haze under a parachute. It touched the surface on the 14th of January 2005. It was the first landing ever made on a moon in the outer solar system. A machine from Earth had come to rest on a frozen world beyond the asteroid belt. This was a triumph of engineering across a distance almost too large to imagine. But there is a detail in that landing worth holding on to. Huygens was allowed to touch Titan freely. No one demanded that it be sterilized against the smallest chance of contaminating the moon. At the time, this was not seen as a danger. In 2005, scientists did not yet know whether Titan or Enceladus could support life. Their potential for habitability was simply unknown. So a lander was permitted to settle onto Titan's surface without the strictest precautions. That permission was granted in a specific moment of ignorance. It would not have been granted a few years later, and the reason it would not is Cassini itself. Because Cassini began to find things. Over its years in orbit, it studied the moons of Saturn one by one. Among them was a small, bright, icy world named Enceladus. It is only a few hundred miles across. From a distance it looks like a clean white pebble, but Cassini flew close, and what it found changed everything about how that little moon was understood. Near the South Pole, Enceladus was venting material into space. Great plumes of vapor and ice grains rose from cracks in its surface. These geysers were not a surface trick, they were fed from below. Cassini's measurements pointed to a global ocean of liquid water hidden beneath the ice. A moon barely wider than a large country was hiding a sea. An ocean beneath the ice is one of the most important things a spacecraft can find. Liquid water is the one condition life on Earth has never done without. Enceladus was spraying that water directly into space, where an orbiting probe could fly through it and taste it. Cassini did exactly that. It passed through the plumes and sampled what they carried. The moon was offering up its hidden ocean without anyone having to land and dig. A world once dismissed as a frozen speck had become one of the most promising places in the solar system to search for life. Titan added to the case. Beneath its haze, Cassini and Huygens revealed a strange and active chemistry. Titan is rich in organic compounds, the carbon-based molecules that on Earth form the building blocks of living things. It has rivers and lakes, though they are filled with liquid methane rather than water. It has weather. It has a cycle of falling and evaporating liquid, like a colder mirror of Earth's own. Titan is not Earth, but it runs a chemistry complex enough to matter. 2 of Saturn's moons had become worlds where the question of life could no longer be waved away, and this is where Cassini sealed its own fate. A spacecraft cannot fly forever. Cassini ran on a finite supply of propellant. Once that propellant was gone, the machine would become uncontrollable. It would still be moving, still looping through the Saturn system, but no longer steerable. No one on Earth could command it to avoid anything. Over long spans of time, an uncontrolled spacecraft can drift, and its orbit can shift, and eventually it can strike something. The something in this case could have been Enceladus, or Titan, or another body carrying the conditions for life. That possibility, however small, was not acceptable. Cassini had been built and launched on Earth. It carried the residue of Earth on its surfaces, the trace microbes that cling to anything made in a laboratory. If a dead, tumbling Cassini were ever to crash into the ocean world it had discovered, it might carry Earth's contamination into a place where life might exist. Scientists could not then tell native chemistry from an earthly stowaway. A future search for life could be poisoned before it began. Planetary protection is the name for the rules meant to prevent exactly this. And those rules demanded that Cassini's small long-term chance of contaminating a habitable moon be reduced to nothing. There was only one way to reduce it to nothing. The spacecraft had to be removed from the system entirely, in a way that left no chance of a later accident. It could not simply be switched off in orbit, because an inert Cassini would keep circling, subject to every gravitational nudge for centuries. It could not be flung outward, because there was not enough fuel to guarantee a clean escape. The safest disposal was also the most complete. Saturn itself would receive the spacecraft. Cassini would be steered into the planet's atmosphere and destroyed. The pressure and heat of Saturn's upper air would take the machine apart and scatter it. Nothing would survive to threaten Enceladus. Nothing would survive to threaten Titan. Consider the shape of this decision. Cassini was doomed not because it failed, but because it succeeded. Huygens had been free to land on Titan, because no one yet knew Titan mattered. Then Cassini proved that Titan mattered, and that Enceladus mattered more. The very discoveries that made the mission historic were the discoveries that made the mission's ending mandatory. A spacecraft found the reasons it had to be destroyed. It handed the argument for its own end to the people who loved it most, and they accepted the argument, because the alternative was to risk one of the most valuable places humanity had ever found. So the destruction was not a tragedy of failure, it was an act of care. The team chose to spend a healthy spacecraft in order to protect the worlds it had revealed. This is why the plunge was authored so carefully. If Cassini had to be sacrificed, then the sacrifice would be turned into science. The machine would not simply be dropped, it would be flown right to the last second, gathering measurements no probe had ever gathered. The moment of disposal would double as the deepest dive ever attempted into Saturn itself. And there was a great deal for such a dive to find. For all its years in orbit, Cassini had studied Saturn mostly from a distance across the barrier of the rings. It had never flown close enough to reach into the space between the rings and the cloud tops. That region held answers that no earlier orbit could touch. How fast does Saturn truly turn deep inside? What is its interior made of? How do the rings and the planets speak to one another through fields and particles? These were old questions, unanswered for decades. The final orbits, and the plunge that ended them, were designed to close the distance and ask them directly. The first surprises came from the gap itself. As Cassini threaded the space between Saturn and its rings, it discovered that the rings are not separate from the planet. They are feeding it. Material rains down out of the rings and into Saturn's upper atmosphere in a steady fall. The amount is not small. Measurements pointed to as much as 10 tons of material every second, drawn from the rings into the planet below. This ring rain carries methane and other organic and hydrocarbon compounds. It carries water. It may carry carbon monoxide as well. The rings, long imagined as a permanent ornament, are slowly emptying themselves into the world they surround. That single finding reframed the whole system. A planet and its rings are not a fixed portrait. They are a slow exchange. The rings are pouring themselves inward, and the planet is receiving them, and the process has almost certainly been running for a very long time. No instrument could have measured this from outside the rings. Only a spacecraft flying through the gap could catch the falling material in the act. Cassini flew through that gap 22 times, and then it flew through one final time and did not come back out. Each pass had sharpened the picture. The last pass would fill in what the others could not reach. Consider what the magnetic field revealed once the spacecraft slipped that close to the planet. Cassini carried a magnetometer, an instrument built to read the invisible field that Saturn generates deep inside itself. From a distance, that field had always looked simple. The grand finale orbits let the instrument read it from barely 2,500 kilometers above the cloud tops. At that range, the simplicity became a genuine puzzle. Saturn's magnetic field is extraordinarily axisymmetric. It is almost perfectly aligned with the planet's spin axis. No other planet shows a field this closely tied to its own rotation. That alignment should not be possible under the rules physicists had trusted. A spinning fluid interior that generates a magnetic field is supposed to tilt that field. The tilt is what lets scientists read a planet's rotation from the outside. Jupiter's field is tilted. Earth's field is tilted. Saturn's field refuses to cooperate. Its magnetic pole sits almost exactly on its geographic pole. For decades, this made one basic question unanswerable. How fast does the inside of Saturn actually turn? The measurements found something subtler still. Saturn's magnetic equator is not centered on the planet. It sits offset toward the north. The field is stronger in the northern hemisphere than in the southern one. That imbalance is a clue about how the field is made and where inside the planet the machinery lives. And within the smooth global field, Cassini detected small, irregular structures. These fine features hint at a second, shallower dynamo running closer to the surface. One field would be generated deep in the metallic hydrogen core region. Another, weaker one might stir in a layer nearer the visible clouds. A planet with two engines instead of one. To answer the rotation question, scientists turned to gravity rather than magnetism. As Cassini fell through the ring gap, the pull of Saturn and the pull of the rings tugged on its path. The spacecraft became a probe of mass itself. By tracking tiny changes in its radio signal, engineers measured how the planet's gravity varied from place to place. Those variations encode the shape of the interior. From that data came a new value for how fast Saturn truly rotates. The deep interior turns once in about 10 hours and 33 minutes. That figure had eluded every earlier attempt. It took a spacecraft weaving between the planet and its rings to pin it down. The same gravity data reached even deeper. It pointed toward the center of Saturn, to the core that no eye will ever see. For a long time, scientists pictured a compact core, a dense ball of rock and ice, sharply bounded, with the gas layered cleanly above it. The grand finale measurements told a stranger story. Saturn's core appears to be diffuse. It is not a hard sphere with a clean edge. It is a fuzzy, extended region where heavy elements blend gradually into the hydrogen and helium above. And it is enormous. The heavy material inside may amount to somewhere between 12 and 20 times the mass of the entire Earth. A core that is not quite solid and not quite gas, smeared across a vast fraction of the planet's inside. A fuzzy core changes how we imagine a giant planet forming. A sharp core suggests a seed of rock that gathered gas around it. A blurred core suggests a more violent, more mixed beginning. Perhaps a great impact stirred the interior long ago. Perhaps the heavy elements were never fully settled. Saturn, it turns out, may still be sorting itself out, even now, billions of years after it formed. The planet is not finished. Its insides are still in slow motion. There was more waiting in the gap. Between Saturn and its innermost bright rings, Cassini found a radiation belt that no one had known was there. It is a narrow belt of high-energy particles, held close to the planet, hidden from earlier observation because the rings themselves had always blocked the view. This belt is fed in an unusual way. Cosmic rays arriving from deep space strike the rings in the upper atmosphere. Those collisions knock loose fast particles that become trapped in the magnetic field. The rings, in other words, help create a private zone of radiation tucked in beside the planet. It could only be discovered from inside, and only a spacecraft on a doomed trajectory would ever fly there. Cassini also traced electric currents running between Saturn and its rings. The planet and its rings are not electrically separate, they are linked. Charged particles flow along magnetic field lines, carrying current down into the atmosphere and back out toward the ring plane. This is part of the same story as the ring rain. Material and energy are moving constantly across the space that looks empty in a photograph. The gap Cassini crossed 22 times was never truly empty. It was a corridor of falling matter, trapped radiation and flowing current. The spacecraft had been swimming through an active exchange, and the closer it flew, the more of that hidden traffic it could measure. Every one of these findings has the same signature. Each required proximity. Each demanded that the spacecraft go where no mission had gone, into the narrow, unmapped region beside the planet. From orbit at a safe distance, Saturn kept its secrets. The rotation period stayed uncertain. The core stayed a guess. The ring rain stayed invisible. The radiation belt stayed unknown. Distance had protected the mysteries as surely as it protected the spacecraft. To answer the questions, Cassini had to give up its safety. The grand finale was not a farewell tour. It was the most aggressive science campaign of the entire 20 years. And it was building toward one final measurement that all the others could only approach. The instruments had sampled the rings from nearby. They had read the magnetic field from close range, but they had never touched the atmosphere itself. Saturn's air had always been something Cassini observed from outside, through cameras and spectrometers, from thousands of kilometers away. The last dive would change that. On the final pass, the spacecraft would not fly over the atmosphere. It would fly into it. For the first time, an instrument would breathe Saturn's gas directly. That instrument was the ion and neutral mass spectrometer. It works by taking in gas and sorting the molecules by their mass. Feed it a stream of atmosphere, and it tells you what that atmosphere is made of, molecule by molecule. For 13 years around Saturn it had studied the plumes of Enceladus and the haze around Titan. It had never once been able to sample Saturn's own air, because Cassini had never flown low enough. Now the plan was to point it straight into the oncoming wind and let it drink. To do that, the spacecraft had to be aimed with care. The instrument had to face forward, into the direction of travel, so the atmosphere would flow directly into its opening. This is why, in the small hours of that final morning, Cassini performed a slow and deliberate roll. It was not a panic maneuver. It was a rehearsed turn, executed to place the mass spectrometer into the flow. The spacecraft was arranging itself to taste the planet as it fell. The timeline of that last morning reads like a countdown written in advance. Cassini crossed the orbit of Enceladus for the final time in the early hours, passing the distance of the very moon whose ocean had helped seal its fate. A little over 2 hours later, the spacecraft began its slow roll, taking about 5 minutes to swing the mass spectrometer forward along its path. Everything was now arranged. The antenna held its lock on Earth. The instruments waited, powered and pointed. The spacecraft was falling toward the cloud tops at a speed almost impossible to picture, and it was falling on purpose. It struck the atmosphere near 10 degrees north of Saturn's equator. It arrived on the day side of the planet, close to local noon, in full sunlight. It came in at an altitude of roughly 1,200 miles above the estimated cloud tops. Its speed relative to the planet was on the order of 70,000 to 77,000 miles an hour. Nothing built by human hands had ever entered Saturn. Cassini was the first, and it would remain the only one for a long time to come. At first, the atmosphere was almost nothing. The outermost gas of a giant planet is thinner than the best vacuum most laboratories can make. But even the faintest breath of gas pushes against a body moving that fast. The spacecraft began to feel a gentle growing drag. Its small thrusters woke to answer it. They started firing at only about 1/10 of their strength. Tiny corrections to hold the antenna steady against the first touch of Saturn's air. For a brief window, the balance held. The spacecraft was inside the planet's atmosphere, still pointed at home, still speaking. The mass spectrometer was sampling. The data was flowing. The measurement everyone had waited 13 years to take was finally being made, in real time, as the spacecraft fell. It could not last. The atmosphere thickened with every mile of descent. The drag that had begun as a whisper became a force the spacecraft could not ignore. The thrusters that had opened at 1/10 of their power would soon be asked for everything they had. Cassini was about to enter a contest it was never designed to win. A brief and violent struggle between a machine the size of a small bus and the outer air of a world 760 times its volume. The struggle would be measured not in hours, and not in minutes, but in seconds. And the spacecraft would keep talking through nearly all of them. Consider the size of the weapons Cassini brought to this fight. The spacecraft carried a set of small thrusters that burned hydrazine, a simple rocket fuel. Each one produced about 1/2 a newton of force. That number is easy to say and hard to feel. So hold a tennis ball in your open hand. The gentle press of its weight against your palm is roughly the push each thruster could make. That was the entire arsenal. A handful of tennis ball nudges, aimed against the outer air of a planet more than 700 times the volume of Earth. The engineers knew the match was hopeless. The point was never to win it. The point was to lose it slowly, and to keep speaking for as long as the losing allowed. For an hour before entry, the thrusters had been working a quieter problem. Saturn's thin upper air was already tugging at the spacecraft, not enough to overwhelm it, but enough to nudge its aim. To hold the antenna steady, Cassini used a method the team called bang-bang control. The spacecraft rocked back and forth by fractions of a degree. The full swing was about 2 milliradians, close to 1/10 of a degree, a motion far too small for any human eye to catch. Every few minutes a thruster would pulse, then fall silent, then pulse again. Julie Webster, who managed spacecraft operations, described it as a constant small correction, a machine leaning first one way and then the other to stay pointed at home. It was patient work. It was also the last easy part of the night. Entry changed the arithmetic. As Cassini sank deeper, the air stopped being a nuisance and became a wall. The drag that had asked for occasional pulses now demanded a steady shove. The thrusters answered. They opened from about 1/10 of their power toward full capacity in roughly 1 minute. That is a startling curve. A system built to make tiny, delicate corrections was suddenly running as hard as it could, and the atmosphere kept pushing harder. There was no reserve beyond full. Once the thrusters reached 100%, the spacecraft had nothing left to give. Everything after that point was borrowed time, and the account was already nearly empty. In the final 20 seconds of the struggle, the thrusters were firing almost without pause, held near full capacity the entire time. Picture that. A cluster of tennis ball pushes, fired in a near-continuous stream, straining to keep a falling spacecraft square to the wind. And for most of those 20 seconds, it worked. The antenna stayed on Earth. The signal kept climbing away from Saturn toward the waiting dishes on the far side of the solar system. The instruments kept reading. The mass spectrometer kept tasting the gas rushing past its opening. Each fraction of a second the balance held was another fraction of Saturn's atmosphere measured directly, for the first time in history, by a machine falling through it. There is a clean way to state how long this contest lasted. From the moment Cassini first met measurable drag, the spacecraft held its orientation and kept transmitting for a total of 91 seconds. That is the whole war. Not an hour, not even 2 minutes. 91 seconds between the first real push of the atmosphere and the moment the thrusters could no longer keep up. In the history of a mission that spanned 2 decades, this was the final chapter, and it was shorter than the time it takes to read a page aloud. The nature of the air itself makes the number stranger. The atmospheric density Cassini fought to entry was not thick by any human standard. It was comparable to the tenuous gas found far above Earth, at the altitude where the International Space Station circles the planet. Astronauts up there move through what we would call a near vacuum. The station orbits for years in that thinness without any sense of wind. So why did the same order of thinness tear Cassini apart in a minute and a half? The answer is speed. Cassini was not gliding. It was falling into Saturn at roughly 4.5 times the speed of the space station. At that velocity, even a whisper of gas becomes a hammer. Drag climbs with the square of speed, so a spacecraft moving several times faster feels a force many times greater from the very same air. What the station treats as empty, Cassini met as a solid current pressing against its side. This is the quiet cruelty of the physics. The thing that destroyed Cassini was not a dense atmosphere. It was an ordinary one, encountered at an extraordinary speed. The spacecraft was not crushed. It was simply moving too fast to stay pointed. Every gram of gas it struck became leverage, twisting at the long body of the probe, working to spin it away from Earth. The thrusters existed to cancel that twist. For 91 seconds they did. Then the twist grew larger than anything half a Newton could answer, and the balance that had held all night finally broke. What happened next unfolded in a span most people would round down to nothing. In its final 8 seconds of transmitted data, Cassini began to tip. Not violently, not in a tumble you could see if you were somehow standing beside it. The spacecraft started to lean slowly backward, the way a tired swimmer's head drifts back before going under. That slow lean was enough. As Cassini tipped, the great dish of its high-gain antenna began to slide off Earth point. The narrow beam that carried its voice started to drift past the planet it was aimed at, and once that beam wandered, the connection could not survive. The loss came in 2 distinct stages, and the order matters. The real science and engineering telemetry, the actual numbers describing the atmosphere and the health of the spacecraft, disappeared first. That data stream needed a strong, well-aimed link to survive the crossing, and it was the first thing the drifting antenna could no longer support. When the data stopped, the mission's direct knowledge of the plunge ended. Everything measured after that instant was measured by a spacecraft that could no longer tell anyone what it found. But the radio itself did not vanish at the same moment. After the data cut out, a bare carrier signal remained. A carrier is the plain radio tone underneath the information, a steady hum with no message riding on it. That naked tone persisted for about 24 more seconds after the data was gone. For those final seconds, the dishes on Earth were still hearing something from Cassini. Not words, not readings, just the sound of a transmitter still switched on, still trying, as the spacecraft rolled away from the sky that could receive it. Then even the carrier faded, and there was nothing. Within those last seconds, something odd appeared in the record. As the signal was dying, a few observers watching the raw radio data noticed a brief flicker of apparent recovery. For an instant the tone seemed to strengthen, as if the spacecraft had somehow righted itself and swung its antenna back toward home. It is a tempting thing to believe, a final act of defiance. A dying machine straining once more toward the planet that built it. But the engineers who later reconstructed the fall found no such moment. The spacecraft had not recovered. It was still tumbling, still falling, still doomed. What the observers had caught was not the main beam of the antenna returning to Earth. It was a side lobe. A radio dish does not send its energy in a single perfect pencil of a beam. The strongest energy goes forward, but weaker echoes of the beam spill out at angles around it, faint copies called side lobes. As Cassini rolled, one of those weaker lobes happened to sweep across the direction of Earth. For a heartbeat, a sliver of that stray energy pointed our way, and the dishes registered it as a small rise in the signal. It was geometry, not resurrection. The spacecraft was not coming back. Its antenna was merely turning, and one of its faint edges brushed past us on the way down. The blip that looked like hope was only the shape of the beam, caught in the act of leaving. So the picture of the ending is precise, and it is worth holding still. First the thrusters ramped to full in about a minute. Then, 91 seconds of holding on, the antenna steady, the data flowing. Then, 8 seconds of the slow backward lean. Then the telemetry gone, and the atmosphere unmeasured from that point forward. Then 24 seconds of a bare tone. Then a stray flicker that meant nothing. Then silence. From the first bite of drag to the last fading of the carrier, the whole descent into loss took only a little over 2 minutes. A 20-year mission ended in the time it takes to boil an egg, and here is the part that reason struggles to accept. All of this, the ramp and the fight and the lean and the last tone, had already happened. It was over before anyone on Earth knew a single second of it. The spacecraft that was tipping backward in these descriptions was not tipping in the present. It had finished tipping long before, in a stretch of time that had already closed. What the dishes on Earth were receiving in real time was the report of a death that was already complete. The signals arriving were true. The spacecraft sending them was gone. To understand how a machine could be destroyed and still speaking, we have to leave Saturn for a moment and follow that signal across the enormous emptiness it had to cross, out to a single antenna waiting in the dark on the far side of the world. The signal left Saturn at the speed of light. That is the fastest anything in the universe can move. Nothing carries a message home more quickly, and yet even at that speed, the distance was cruel. Saturn on that morning sat close to 1.5 billion kilometers from Earth. In older units that is roughly 930 million miles. Light does not cross that gulf in an instant, it takes its time. The final report from Cassini needed about 83 minutes to arrive. That is nearly an hour and a half of pure travel. For all of that time the signal was alone in space, carrying news that no one had yet heard. Think about what that number means. When Cassini first met measurable drag, the message of that moment began its long fall toward us. But the spacecraft did not wait for the message to land. It kept fighting, kept leaning, kept firing. It finished dying while its first distress was still in transit. Every stage of the end was like this. The ramp to full thrust, the 91 seconds of control, the last 8 seconds of tipping, the bare tone that followed. Each of these happened, then travelled, then finally reached an antenna long after the event was closed. The spacecraft was always ahead of its own story. There is a strange grace in that gap. Cassini's program manager, Earl Mays, understood it before the plunge ever began. He described the final signal as something like an echo. He said it would radiate across the solar system for nearly an hour and a half after Cassini itself had gone. That was not poetry stretched over the facts. It was a plain description of the physics. The voice would outlive the throat. The word would outlive the mouth that shaped it. For almost 90 minutes, a dead machine would still be speaking to anyone who cared to listen. So the signal fell across the dark, past the orbit of Jupiter, past the cold, empty stretches between the outer planets, down toward a small blue world turning quietly under its own weather. And it aimed at a single point on that world. Not a country, not a city, a dish. To catch a whisper this faint, from this far, you cannot simply point a receiver at the sky. You need one of the largest and most sensitive antennas ever built. You need the Deep Space Network. The Deep Space Network is a set of enormous radio antennas spread around the planet. They are placed roughly evenly around the globe, so that as Earth turns, at least one of them can always face deep space. On that morning, the duty fell to Australia. The station sat outside Canberra, in the dry hills of the southern continent. There, a great dish 230 feet across, about 70 meters wide, stood tilted toward Saturn. It listened for a signal weaker than almost anything else humans try to detect. The power arriving from Cassini was smaller than the light of a distant star. The dish gathered it anyway. For years these antennas had been Cassini's only tie to home. Every image, every measurement, every heartbeat of the spacecraft had come down through dishes like this one. Now the same network waited for the last of it. Engineers watched their screens. A thin line traced the strength of the incoming carrier. As long as that line held, something of Cassini still reached across the void. When it fell, there would be nothing more. Ever. The line held through the roll. It held through the first bite of the atmosphere. It held through the ramp to full thrust. It wavered as the spacecraft began to lean. Then the data stopped, and only the bare tone remained. Then even the tone thinned and broke. On the screens in Australia and in mission control, the trace dropped to noise. The listening was over. Loss of signal was confirmed at Canberra at 55 minutes and 46 seconds past 7 in the morning, Eastern Time in the United States, in the local reckoning of the wider world that was just before noon in Coordinated Universal Time. But that stamp of the clock records only when the news reached the dish. It does not record when Cassini died. By the plain arithmetic of the distance, the spacecraft had been gone for about 83 minutes already. It had broken apart, heated, and scattered into Saturn's sky more than an hour before the antenna fell quiet. The people watching the trace collapse were not watching a death. They were watching the arrival of a death that had already finished. This is the hardest idea in the whole account, and it is worth holding still. There is no way to shorten that delay. There is no faster channel. The universe sets the speed of the message, and the message could not beat the light that carried it. So the moment of loss on Earth and the moment of loss at Saturn were separated by the width of the solar system. For that final stretch of time, two truths were both real. On Earth, Cassini still spoke. At Saturn, Cassini no longer existed. The gap between those truths was the echo Earl Mays had promised. Now turn from the antenna in the desert to the room where the mission lived and ended. At the Jet Propulsion Laboratory in California, it was still early. More than 1,500 people had gathered. Some were scientists who had built careers on this one spacecraft. Some were engineers who had nursed it through failures and close calls across 2 decades. Some were family, brought in to witness the last morning. They stood in front of the same falling line that the engineers in Australia watched. They had lived their working lives waiting for signals from this machine. They were about to wait for the last one. When the trace dropped and stayed down, Earl Mays spoke into the quiet. He said that the Cassini mission had ended that morning, high over the clouds of Saturn, and that the spacecraft was gone. He thanked it. He called it a faithful explorer and bid it farewell. Then he said simply that the project manager was off the net, and he lifted the headset from his ears. It was the plainest possible way to close a mission. No drama larger than the facts, just a man reporting that the work was finished and the machine would not answer again. The room did not stay silent. More than 1,500 people applauded. They reached for one another. Some wept and did not try to hide it. They were mourning a robot that had never felt a thing, that had no idea it was loved, that had followed its instructions to the last thruster pulse without knowing any of them. And yet the grief was honest. For 20 years this spacecraft had been their eyes and hands at a world no human will visit in this lifetime. When it stopped, a way of seeing stopped with it, and here is the fact that turns the grief into something almost defiant. Cassini did not go quietly to be rid of it, it went to work. In those final minutes, 8 of its 12 science instruments were switched on and gathering data. This was not a shutdown, it was one last experiment, run at the cost of the experimenter. Chief among the working instruments was the ion and neutral mass spectrometer, the tool that had been rolled forward to face the oncoming flow. As the atmosphere rushed in, that instrument tasted it. It measured, directly, the actual gas of Saturn's upper air. No probe had ever done that before. For the first time, a machine sampled Saturn's own atmosphere in place, from inside, while falling through it. The other working instruments were listening too, each in its own way. Magnetic sensors read the field. Plasma detectors counted charged particles. Together they reached deeper into Saturn than any spacecraft ever had. These were the deepest direct measurements ever made of the planet's plasma, its magnetic field, its temperature and the composition of its air. And Cassini did not hoard them for a later download that would never come. It sent them home as it collected them, in nearly real time, streaming the readings back through the same antenna it was struggling to keep aimed at Earth. The fight to hold that antenna steady was in part a fight to keep the data flowing. Every second the thrusters bought was another second of science pushed across the gulf before the lean finally won. So the last 20 minutes were not an ending in the ordinary sense. They were a first. A spacecraft designed to look at Saturn from a distance became, in its final act, a spacecraft that touched Saturn from within. It converted its own destruction into the one measurement it could never have made while intact. The plunge that killed it was also the only path to the data. To learn what the upper atmosphere was made of, the machine had to enter that atmosphere. To enter it at that speed was to die. Cassini did both in the same motion. That is why the applause in that room carried something other than sorrow. The people there knew what the falling line meant. It meant the spacecraft was gone, but it also meant the plan had worked to its very last second. The probe had held its aim long enough. It had tasted the air. It had sent the numbers home. It had failed only when failure became physically unavoidable, and not one moment sooner. There are worse ways for a machine to end than in the middle of doing exactly what it was made to do. But a question sits underneath all of this, and it has not yet been answered. Why did any of it have to happen at all? Cassini still had working instruments. It still had a voice. It was healthy enough to run experiments while it burned. A spacecraft in that condition is not usually thrown into a planet on purpose. Something had made this deliberate destruction not just acceptable, but required. To understand that choice, we have to go back years before the plunge, to 2 small moons, and to what Cassini itself had found waiting on them. The first of those 2 moons is Enceladus. It is small and bright and wrapped in clean white ice. For years it looked like a quiet, frozen world with little to say. Then Cassini turned toward its southern pole and saw something no one expected. Long parallel cracks ran across the ice near the south. From those cracks, fountains of water vapor and fine ice grains rose high into space. That was the first clue. A small frozen moon was actively spraying water off its own surface. The question became where that water was coming from. Cassini flew through the plumes and sampled the material they carried. The evidence favored a global ocean of liquid water hidden under the ice of Enceladus. A body of water, dark and buried, circling Saturn on a tiny moon, and it was venting some of that ocean into space, where a passing spacecraft could taste it directly. This changed what Enceladus meant. Liquid water and organic chemistry are ingredients scientists look for when they ask whether a place could support life. No one claimed to have found life there. That is a different and far heavier claim. But Enceladus had moved from a frozen curiosity to a world worth protecting. Its buried ocean was now one of the most interesting places in the solar system. The second world is Titan, the largest of Saturn's moons and one of the strangest Cassini studied. On Titan, the spacecraft found complex organic chemistry. It was the kind of carbon-rich chemistry that interests anyone asking how life begins. Titan is bitterly cold and utterly unlike Earth, but its chemistry echoes the chemistry that may have come before life on our own world. It became a natural laboratory for those questions, sealed far out in the cold. So Cassini had found two nearby worlds that mattered in a new way. One held a hidden ocean, the other held rich organic chemistry. And Cassini, after 2 decades in space, was running low on the fuel it used to steer. This is where the danger appears. A spacecraft that cannot steer cannot be aimed. Once its fuel was gone, Cassini would drift, pushed by gravity along paths no one could fully control. Over many years, one of those paths could end with the spacecraft striking a moon. That possibility was small, but it was not zero, and the concern was not the crash itself. The concern was contamination. Spacecraft built on Earth carry earthly microbes, however carefully they are cleaned. A few of those microbes are tough enough to survive long exposure to space. If a dead drifting Cassini eventually fell onto Enceladus or Titan, it might carry Earth life to a place that could, in theory, host it. That would ruin the very question those moons were now precious for asking. A future mission searching for native life could find only the life we brought by accident. This is the rule that decided Cassini's end. It is cold, planetary protection. The idea is simple to state and heavy to follow. When exploring a world that might support life, do not contaminate it. To honor that rule, planners had to remove any long-term chance that Cassini could fall onto one of those moons. The cleanest way to guarantee that was to choose the spacecraft's grave in advance. Send it into Saturn itself, at high speed, where it would burn and break apart in the atmosphere. Destruction was not a failure of the plan. Destruction was the plan. There is a quiet irony inside this decision. Years earlier, Cassini had carried a lander to Titan and released it. The Huygens probe descended through Titan's air and touched down on the surface in January of 2005. It was the first landing ever made on a moon in the outer solar system, and it landed with none of the fear that later doomed its mothership. At that time, no one knew what Cassini would go on to discover. The chemistry of Titan and the ocean of Enceladus were still unknown. Titan did not yet count as a world that needed strict protection. So Huygens was allowed to land. It was Cassini's own discoveries that changed the rules. By finding the plumes of Enceladus and the organic chemistry of Titan, Cassini raised the value of those moons. In doing so, it helped write the very standard that would require its own destruction. The spacecraft learned enough about Saturn's moons to make itself too dangerous to leave behind. Few missions end this way. Cassini was sentenced by its own success. Understanding this changes how the final dive should be read. The plunge was not a machine simply breaking down at the end of a long life. It was a controlled sacrifice, chosen deliberately to keep 2 fragile worlds clean. And the planners made one more decision that turned the ending into science. If the spacecraft had to be destroyed inside Saturn, then it should gather data on the way down. It should point its instruments outward and study the planet from inside its own atmosphere, in places no probe had ever reached. The grave became a final experiment. That final experiment was part of a larger campaign. The dives through the gap between Saturn and its rings let Cassini measure the planet more closely than ever before. What it found there rewrote parts of what scientists thought they understood. One discovery concerned the rings themselves. Cassini measured material falling from the rings into Saturn's upper atmosphere. The rings were raining into the planet. The amount was large. As much as 10 tons of material fell every second. A steady drizzle of water and organic compounds pulled down from the rings. This ring rain suggests the rings are not permanent. They are slowly feeding themselves into the planet over time. The closed passes also let Cassini read Saturn's magnetic field from very near the cloud tops. On those orbits, it flew roughly 2,500 kilometers above the clouds. The field it measured was strange in a specific way. It was extremely well aligned with the planet's spin axis, far more aligned than theories of how such fields form would normally allow. A planet's magnetic field is usually tilted against its rotation. Saturn's is almost perfectly straight. That near-perfect alignment is a genuine puzzle, because it is hard to build and sustain a field like that. Cassini also found the magnetic equator sitting slightly north of the physical equator. It saw hints of smaller magnetic structures that suggest activity closer to the surface than expected. Even the length of Saturn's day came out of these final measurements. Saturn is a ball of gas with no solid surface to watch, so its true rotation had been hard to pin down. By combining the finale data, scientists estimated the deep interior turns once in about 10 hours and 33 minutes. The same measurements reached toward the center of the planet. They pointed to a core that is not a hard sphere, but a diffuse, fuzzy region, blended into the layers around it. Inside that region sits a great mass of heavy elements, something like 12 to 20 times the mass of the entire Earth, mixed through Saturn's deep interior rather than sitting in a neat ball at the middle. There was more hidden in the gap between planet and rings. Cassini found a belt of high-energy particles there that no one had known was present. It forms in an unusual way. Cosmic rays from deep space strike the rings, and those collisions knock loose particles that become trapped near the planet. The rings, in effect, help create a private radiation belt tucked close to Saturn. Cassini also traced electric currents flowing between the planet and its rings. The rings are not a separate passive decoration. They are wired into Saturn, exchanging material and energy with the world they circle. Then there was the atmosphere itself, sampled directly in the final minutes. As the spacecraft fell, its mass spectrometer faced into the oncoming gas and read what Saturn is made of at that height. This was the first time any instrument had tasted Saturn's atmosphere from the inside. Every earlier study of the planet's air had been made from a distance. Now a spacecraft was breathing the gas directly and sending the results home while it still could. Those readings reached the deepest layers Cassini ever touched. They captured the composition, the density, and the temperature of a region no instrument had entered before. It is worth holding both facts together at once. Everything measured in that final descent came from a machine that was in the act of being destroyed. The ring rain, the magnetic field, the length of the day, the buried core, the hidden radiation belt, the taste of the atmosphere. All of it flowed from an instrument falling toward its own end. The science and the destruction were not separate events. They were the same event. To feel the weight of that ending, it helps to remember how the journey began. Cassini left Earth on the 15th of October, 1997. It rose on a Titan rocket from Cape Canaveral, carrying the European Huygens probe folded against its side. It did not fly straight to Saturn. The distance was too great to cross quickly, and the cruise took years. It was not until the 1st of July, 2004, that Cassini finally slowed itself into orbit around the planet. In that moment, it became the first spacecraft in history to circle Saturn. From there, it stayed. It circled the planet for 13 years. It flew past moons again and again. It released the Huygens probe toward Titan and followed its descent. It mapped a system of rings and moons in a detail no one had ever seen. 2 decades separated the launch from the final signal, and all of that history pressed down into the handful of minutes when it fell. Yet the ending did not answer everything. In many ways, it deepened the questions. The buried ocean of Enceladus is still there, still venting into space, still untouched by any instrument built to search for life. Cassini could taste the spray, but it was never designed to say whether anything lives in that water. Titan keeps its heavy organic chemistry, waiting for a return. The strange straightness of Saturn's magnetic field still resists easy explanation. The fuzzy core and the true age of the rings remain open problems that scientists continue to argue over. Cassini closed one chapter and left several others standing open. Its final descent was not the last word on Saturn. It was the last word from this particular explorer, and the two are not the same. And yet the descent was not only a farewell, it was also a measurement. Every earlier orbit had studied Saturn from a careful distance. The plunge did something no orbit could. It carried a working laboratory into the planet itself. For a few final minutes, Cassini stopped observing the atmosphere from above and began to touch it. That distinction matters more than it first sounds. A telescope can watch a candle across a room. Only a hand held to the flame can feel its heat. Cassini, in the end, put out its hand. The instrument that mattered most in those minutes was the ion and neutral mass spectrometer. Scientists call it the mass spectrometer, or simply the sampler. It works by drawing in gas and sorting the particles by their mass. Lighter molecules and heavier molecules separate cleanly. From that pattern, the composition of a gas can be read. For 13 years the instrument had tasted the thin material near Saturn's moons. Now it was pointed forward, straight into the oncoming rush of the planet's own upper air. This was the first time any instrument had directly sampled Saturn's atmosphere in place. Not inferred it from a distance, not modelled it from colour and light, tasted it, molecule by molecule, as the spacecraft fell. What the sampler found did not simply confirm the textbooks, it complicated them. The upper atmosphere held more than hydrogen and helium, the two gases that make up most of Saturn. It carried heavier compounds that should not have been so abundant so high. Some of that material was not rising from below, it was falling from above. Cassini had walked into a slow, steady rain that no one had fully expected. This is the phenomenon scientists now call ring rain. Saturn's rings are not a permanent decoration, they are leaking. Material drifts inward from the rings and drops into the planet's upper atmosphere in a continuous stream. The finale measurement suggested the flow could reach as much as 10 tons of material every second. Not 10 tons in a day. 10 tons in a single second, falling endlessly. The rain carried methane and other organic and hydrocarbon compounds. It carried water. It may have carried carbon monoxide as well. The rings were feeding the planet, quietly, all the time, and no spacecraft had ever been close enough to catch it in the act. Consider what that means for the rings themselves. If they are losing material at that rate, they are not eternal. They are being spent. A structure that looks fixed and ancient in a photograph is in fact draining into the planet below it. Cassini could not settle exactly how old the rings are, or how long they have left, but it delivered the hard evidence that the question is real. The rings have a budget, and the budget is running down. The second great puzzle came from the magnetic field. Every earlier orbit had measured Saturn's magnetism from far out. The finale orbits brought Cassini in close, skimming roughly 2,500 kilometers above the cloud tops. From that height, the magnetometer read the field with a precision no one had reached before. And the field it measured was strange in a very specific way. It was almost perfectly aligned with the planet's spin axis. That alignment sounds tidy. In fact, it is a problem. A planet generates a magnetic field through a churning, electrically active interior, a process called a dynamo. Simple theory says a working dynamo should produce a field that is tilted away from the rotation axis, at least slightly. Earth's field is tilted. Jupiter's field is tilted. Saturn's field, as far as Cassini could measure, is not. Its magnetic axis and its spin axis sit almost on top of each other. The magnetic equator does not even lie on the physical equator. It is offset toward the north. A field this symmetric is not what a straightforward dynamo should make, and Saturn insists on making it anyway. The measurement did more than deepen the mystery. It also broke a tool that scientists had counted on for years. On most planets, the tilt of the magnetic field gives away the length of the day. The field sweeps around like the beam of a lighthouse, and the sweep can be timed. At Saturn, with no meaningful tilt, that lighthouse hardly turns. For a long time, no one could agree on how long a Saturn day even was. The planet is wrapped in featureless cloud. Its magnetic field would not cooperate. The most basic number about a world, the length of its day, stayed uncertain far longer than it had any right to. Cassini answered that question from a different direction. During the finale, the spacecraft measured tiny variations in Saturn's gravity and studied faint waves rippling through the rings. Those ring waves act like a seismograph. They respond to the planet's interior stirring beneath them. By reading the rings, scientists could infer how the deep interior rotates. The answer came out to about 10 hours and 33 minutes. A Saturn day is a little under half an Earth day. That number was won not by looking at the planet, but by listening to what the planet did to its own rings. The same close approach let Cassini feel its way into Saturn's core. By tracking exactly how the planet's gravity tugged on the falling spacecraft, scientists could probe the mass hidden at the center. What they found was not a simple hard ball of rock and metal. The evidence pointed to a diffuse core. Some describe it as fuzzy. Instead of a sharp boundary between a solid center and the gas above it, the heavy elements appear to be smeared out, blending gradually into the surrounding hydrogen. That fuzzy core seems to hold somewhere between 12 and 20 times the mass of the entire Earth in heavy material, spread through the deep interior rather than packed into a single point. A fuzzy core changes how we imagine a giant planet forming. A clean core suggests heavy material gathered first and gas piled on afterward. A smeared core suggests a more tangled history, with mixing that never fully settled. Saturn, it turns out, may not have a tidy layered structure at all. It may be blurred all the way down. Cassini could not resolve every detail, but it narrowed the possibilities in a way remote observation never could. There were smaller discoveries folded into those same final orbits, and some were entirely new. Cassini found a radiation belt no one had known was there. It sits very close to the planet, in the region the spacecraft was now crossing for the first time. This belt is made by cosmic rays, high-energy particles from deep space, slamming into the rings and the upper atmosphere and knocking loose showers of new particles. Because the belt hugs the planet so tightly, tucked inside the rings, every earlier orbit had passed it by. Only by threading the gap could Cassini feel it. The spacecraft also detected electric currents flowing between Saturn and its rings. The planet and its rings are not electrically separate, they are connected. Charged material moves along magnetic field lines, linking the atmosphere to the ring system in a slow circuit. This is part of the same story as the ring rain. The rings are not a still, silent hoop of ice. They are in constant electrical and physical conversation with the planet, exchanging particles and current, feeding and draining in ways that were invisible until a spacecraft flew through the space between them. Taken together, the finale returned the deepest direct measurements ever made of Saturn, the deepest reading of its plasma, the charged gas that fills the space around it, the deepest reading of its magnetic field, the deepest reading of its temperature and its composition. Every one of those records was set in the closing stretch of the mission, and several were set in the very last dive, as the sampler drank the upper atmosphere and the antenna held its aim toward Earth. The most valuable science of a 20-year mission came in its final hours, from a region the spacecraft could only reach by agreeing not to come back. That is a hard thing to hold in the mind. The measurements were priceless precisely because they were fatal. Cassini could not have made them from a safe orbit. To sample the atmosphere directly, it had to enter the atmosphere. To feel the radiation belt inside the rings, it had to fly inside the rings. Each new fact was paid for with distance the spacecraft could never recover. The science and the destruction were not two separate events. They were the same event, read from two sides. And the data behaved exactly as the design intended. As Cassini fought the thickening air, the sampler kept swallowing gas and the radio kept sending. The numbers streamed home in near real time, because there would be no later chance to store them and play them back. Whatever the instruments learned in those minutes had to leave the spacecraft immediately, or it would be lost with it. So the final measurements did not sit in a recorder waiting for a download that would never come. They flew ahead of the wreck, outrunning it, already crossing the solar system while the machine that made them was tearing apart. That is why the loss of the spacecraft did not mean the loss of the science. The two were separated by the speed of light, and by a careful choice made years before. The instruments spoke as they died, and their words had already left. Somewhere in that stream were the first direct notes on Saturn's outer air, the fingerprint of the ring rain, the pressure and the temperature of a place no probe had ever entered. The plunge was an ending for the machine. For the data, it was a beginning, a set of numbers that scientists would still be studying long after the last carrier tone had faded from the antenna at Canberra. Consider what one of those instruments was built to do. The mass spectrometer aimed into the oncoming wind did not photograph Saturn's air, it tasted it. Gas rushed into a narrow opening at tens of thousands of miles per hour. Inside, molecules were sorted by their weight and counted one kind at a time. This is the oldest ambition in planetary science made suddenly literal. For decades, Saturn's upper atmosphere had been studied from a distance. Its composition was inferred from light, from color, from the way sunlight bent as it passed through the haze. Now a machine was standing inside that atmosphere and reading it directly. Every second of survival added new entries to a list no one had ever been able to write. The reward for reaching so deep was measured not in beauty, but in precision. The list held surprises. Scientists had expected a fairly clean upper atmosphere, mostly the light gases that dominate a giant planet. What the instrument found instead was a place cluttered with heavier material that had no business being there. Complex molecules appeared where simple ones were predicted. The air near the top of Saturn was contaminated, and the contamination was falling from above. The rings themselves were bleeding into the planet. This was not a slow trickle at the edge of detection. The measurements pointed to a steady rain of material pouring down out of the rings and into the atmosphere below them. The scale of that rain is difficult to hold in the mind. The estimates reached as high as 10 tons of material every second. Water was part of it. So were methane and other organic compounds, the carbon-rich molecules that make a planet's chemistry interesting. Some of it may have been carbon monoxide. All of it was leaving the rings and entering Saturn, second after second, a quiet erosion happening in plain sight. The rings that look permanent from Earth are not permanent at all. They are feeding the planet they circle, and the spacecraft that measured this was doing so from inside the very column of falling material on the last morning it would ever operate. This changed a simple question into an urgent one. If the rings are raining into Saturn at that rate, how long can they last? A structure that loses 10 tons a second is a structure with a clock attached to it. The finale data did not settle the argument, but it sharpened it. The rings may be far younger than the planet, and they may be temporary features that will one day thin and vanish. We may be living in the narrow window of time when Saturn has rings at all. The spacecraft did not begin its mission to answer that. It answered it anyway in its final descent, by flying through the answer. Other instruments were reading other things. The magnetometer, which measures magnetic fields, had been carried through the ring gap on every finale orbit, passing only about 2,500 kilometers above the cloud tops. From that close it could feel the planet's magnetic field with a clarity no earlier pass had allowed. What it found was almost too clean. A planet's magnetic field is generated deep inside it, and the field usually leans, tilted away from the axis the planet spins around. Earth's field leans. Jupiter's field leans. Saturn's field, measured from close range, barely leans at all. It is astonishingly aligned with the planet's own rotation, more symmetric than any theory of how such fields form had comfortably predicted. That symmetry is a genuine problem, and scientists say so plainly. The leading understanding of planetary magnetism holds that a perfectly aligned field should not be able to sustain itself. Some tilt is thought to be necessary for the churning interior to keep the field alive. Saturn appears to break that expectation. The finale measurements did not explain how. They confirmed that the puzzle is real and made it harder to wave away. Hidden inside the symmetry were smaller magnetic structures, faint irregularities that hinted at a second, shallower layer of churning fluid nearer the surface than the deep engine. A planet may run more than one dynamo at once. The idea remains unproven, but the close data gave it something firm to stand on. There was another prize buried in these final orbits, and it concerns a question that sounds almost too basic to still be open. How fast does Saturn turn? For a rocky planet, the answer is easy. You watch a mountain go around. Saturn has no mountains and no fixed surface, only bands of cloud that move at different speeds and hide the true rotation of the body beneath. For years, the planet's day was uncertain by many minutes, an embarrassing gap in the record of a world we had orbited for over a decade. The finale offered a new way in. By reading the planet's gravity and the subtle waves that its interior raises in the rings, scientists could reach past the clouds to the deep rotation itself. The answer that emerged was close to 10 hours and 33 minutes. A day on Saturn, finally pinned down not by watching the weather, but by listening to the planet's own structure. The same gravity data reached even deeper, down to the core. A giant planet was long imagined to hold a compact ball of heavy elements at its center, a hard seed wrapped in enormous layers of gas. The finale measurement suggests something stranger. Saturn's core appears to be diffuse rather than sharp, a fuzzy region where heavy material and lighter gas blend together over a vast distance, instead of separating cleanly. Inside it may lie something like 12 to 20 times the mass of the entire Earth in heavy elements, not packed into a stone, but smeared through a huge fraction of the planet's interior. A world with no firm center, only a gradual thickening toward the middle. The spacecraft never touched that core. It felt its pull, and its pull described a shape no one had drawn before. The close passes revealed features that had been completely unknown. A previously unseen belt of radiation was found hugging the planet, formed where cosmic rays from deep space slam into the rings and knock loose a shower of energetic particles. There were electric currents running between Saturn and its rings, invisible threads of moving charge linking the planet to the structure around it. None of this had been mapped, because nothing had ever flown through the gap to map it. The region between Saturn and its rings had been, until the finale, a blank space on the chart. The spacecraft spent its final months turning that blank into a record, and its final minutes adding the deepest entries of all. All of this rested on a decision made years before the plunge, and the decision was not about physics. It was about protection. Somewhere in its long tour, the spacecraft had discovered that one of Saturn's small moons hides a global ocean of liquid water beneath its icy shell. That moon vents its ocean into space through cracks near its south pole, throwing plumes of water and ice and organic molecules out where a passing spacecraft can fly through them and sample them. Another of Saturn's moons, the large hazy one, was found to hold a rich chemistry of carbon compounds under its clouds. Two worlds, both suddenly interesting to anyone asking where life might be possible. And circling near them, a spacecraft that would one day run out of fuel. That combination created an obligation. A spacecraft with no fuel cannot steer. A machine that cannot steer will eventually drift wherever gravity carries it, and over long enough time it could fall onto one of those moons. It would arrive carrying whatever microbes had survived from Earth, hitchhikers baked onto its surface since launch, and it could plant them in an ocean that might harbour a chemistry of its own. The scientific cost of that accident would be permanent. A future mission searching for life could no longer trust what it found, because the contamination might have come from us. To rule that out, the spacecraft had to be removed while it could still be aimed. The only clean destination was the planet itself, whose crushing atmosphere would erase every trace of Earth in seconds. There is a hard symmetry in that reasoning. The spacecraft was destroyed precisely because of what it discovered. Had it never found the ocean, had it never read the plumes, there would have been no ocean worth protecting, and no rule requiring the plunge. The success of the mission wrote its own death sentence. The probe that had ridden down onto the large moon years earlier had faced no such restriction, because at that time, No one yet knew those worlds might be habitable. It was the spacecraft's own findings that raised the standard, and the raised standard came back to claim the spacecraft that raised it. The machine ended itself to keep safe the discoveries it had made. So the final dive was not a crash in the ordinary sense. It was the last deliberate command in a long chain of deliberate commands. Point the antenna at Earth. Turn the instrument into the wind. Hold the line as long as the thrusters can hold it. Send everything. Keep nothing. Let the numbers leave before the machine does. Every one of those choices had a reason, and every reason traced back to the same principle. The mission mattered more than the spacecraft. The data mattered more than the machine. The knowledge had to survive even if nothing else did. And it did survive. It crossed the gap between the planet and its rings for the last time, entered the atmosphere no probe had entered, tasted the air, felt the field, weighed the core, and then handed all of it forward into a stream of radio light already racing home across 1 billion miles of empty space. And what left was not a story. It was a column of numbers, cold and precise, the kind of measurement no earlier probe had ever taken. The ion and neutral mass spectrometer had been turned to face the oncoming gas. As Cassini fell, that instrument breathed in Saturn's upper atmosphere directly. It counted molecules one by one. It weighed them. It reported what the air of a giant planet is actually made of, sampled in place, at the source, for the first time in history. No telescope had done this. No flyby had done this. Only a spacecraft willing to fall could do this. And Cassini was falling. The numbers held a surprise that scientists are still working through. The rings above Saturn are not permanent. They are leaking. Material drains steadily out of the rings and down into the planet below. Cassini measured that rain as it happened. As much as 10 tons of matter fall from the rings into Saturn's atmosphere every second. It is not only water, it carries methane. It carries other organic and hydrocarbon compounds. It may carry carbon monoxide as well. Scientists named the effect ring rain. Before the grand finale, ring rain was a suspicion. After the final dives, it was a measurement. This changes how we think about the rings. A structure that looks eternal is instead a structure that is emptying. The rings feed the planet. The planet slowly consumes the rings. Cassini could not tell us exactly how long the rings will last, but it told us the leak is real and the rate is large. A bright band of ice and dust that has watched over Saturn for ages is quietly falling apart, and it is falling apart into the very air the spacecraft died tasting. The magnetometer told a stranger story. Every spinning planet with a magnetic field is expected to tilt that field away from its axis of rotation. Earth does this. Jupiter does this. The tilt is what makes a planetary dynamo possible in most theories. Saturn refuses. Its magnetic field is almost perfectly aligned with its spin. During the close passes above the cloud tops, Cassini measured that field from nearer than any craft had ever been. The field was extremely axisymmetric. Its magnetic equator sat slightly north of the planet's true equator, and within that clean field, Cassini found faint small-scale structures. Those small structures matter. A magnetic field this smooth should not exist under the rules scientists use. Yet the tiny wrinkles Cassini detected hint at a second, shallower dynamo working somewhere in Saturn's outer layers. A deeper engine may generate the main field. A shallower engine may add the fine detail. This is a leading interpretation, not a settled fact. But it is an interpretation built on data taken during a controlled fall through the field itself. The spacecraft measured the puzzle from the inside as it died. The gravity measurements reached deeper still. By tracking exactly how Saturn's pull tugged on Cassini during each finale orbit, scientists read the shape of the mass hidden below. 2 answers came out of that reading. The first was the length of Saturn's day. For decades, the true rotation period had been uncertain, because a gas planet shows no fixed surface to time. The finale data settled it near 10 hours and 33 minutes. A planet more than 9 times wider than Earth turns once in less than half an Earth day. The second answer was the core. Scientists had long pictured a small hard center buried under thousands of miles of hydrogen. The gravity data pointed to something softer and larger. Saturn appears to hold a diffuse core, a fuzzy region rather than a sharp ball, spread across a wide part of the interior. Inside it sit roughly 12 to 20 Earth masses of heavy elements, blended into the surrounding hydrogen rather than sealed beneath it. The heart of Saturn is not a stone, it is a gradient. It fades from rock and metal into gas without a clean edge. There was more that the finale returned. Threading the gap between the planet and the rings, Cassini crossed a region no craft had entered. There it found a previously unknown radiation belt, one hidden inside the main rings. Cosmic rays strike the ring particles and knock loose fast-charged particles, and those particles form a belt that earlier missions never saw because they never flew close enough. The spacecraft also traced electric currents linking Saturn to its rings, a flow of charge connecting the planet to the bands that circle it. The rings are not a passive decoration, they are wired into the world they orbit. Hold the scale of this for a moment. Almost every number here came from the last months of a mission that had already run for 13 years at Saturn. The rotation period, the fuzzy core, the ring rain, the hidden radiation belt, the wired currents, the clean and puzzling field. These are not footnotes. They are among the most important results Cassini ever produced, and the spacecraft gathered them by going where staying alive was impossible. It spent its final orbits earning discoveries that a safer plan could never have reached. Then it spent its final minutes tasting the atmosphere that ended it. This is the part that makes the ending feel less like a loss. The dive was not wasted, the dive was the experiment. For the whole life of the mission, Saturn's upper atmosphere had been out of reach. You cannot sample air without entering it. You cannot enter it without falling. And you cannot fall without ending. So the only way to measure the thing Cassini most wanted to measure was to accept that measuring it would be the last thing the spacecraft ever did. The engineers understood this trade years in advance. They chose the science and accepted the cost. And behind that choice stood a harder reason, one that had nothing to do with curiosity and everything to do with care. Cassini did not have to die inside Saturn. It could have been left to drift. But drifting was the danger. Over the years, Cassini had discovered that Saturn's moons are not dead worlds. Beneath the icy shell of Enceladus, it found a global ocean of liquid water. It watched that ocean vent into space through cracks near the moon's south pole, throwing plumes of water and salts and organic traces into the dark. On Titan it found rivers, lakes and rain, and a thick atmosphere rich with complex organic chemistry. 2 moons in one system, each holding ingredients that life might use. That discovery placed a burden on the discoverer. Cassini carried no sterile guarantee. It had been built and launched before anyone knew these moons could matter this way. If the spacecraft ran out of fuel and lost control, it would keep orbiting for years, unsteerable, its path slowly bending under the pull of Saturn and its moons. Given enough time, a dead and tumbling Cassini could drift into Enceladus or Titan and strike the surface. Even a tiny chance of that was too much. A single hardy microbe from Earth, carried across 1 billion miles, could poison the very question the mission had opened. Are we alone? You cannot answer that question if you contaminate the place you meant to ask it. There is a quiet irony folded into this. When the mission first arrived, it dropped the European Huygens probe onto Titan in early 2005, the first landing ever made on a moon in the outer solar system. That landing raised no alarm at the time, because no one yet knew Titan might be habitable. It was Cassini's own later findings that changed the rules. The spacecraft revealed the oceans and the chemistry that made these moons worth protecting, and in revealing them, it wrote the very safety standard that would one day demand its own destruction. The explorer uncovered the treasure, then was required to remove itself so the treasure would stay clean. so the plunge was mercy as much as sacrifice. NASA did not throw the spacecraft away. It guided the spacecraft to the one place where it could do no harm and still do good. Saturn's crushing atmosphere would tear Cassini apart and heat every fragment past the point where anything living could survive, if anything living had ever been aboard. The planet itself took nearly 7 years. It swung past Venus twice, past Earth once, past Jupiter, each pass stealing a little speed from a planet to build its own. It reached Saturn in the summer of 2004 and slid into orbit on the 1st of July, the first spacecraft ever to circle that world. From that arrival to the final dive, 13 years passed. From launch to loss of signal, nearly 20. Every discovery of the finale rested on that long approach. The instrument that tasted the atmosphere had been calibrated across 2 decades of flight. The gravity readings that found the fuzzy core came from a craft that had learned Saturn's pull orbit by orbit. The magnetometer that mapped the strange clean field had trailed through that field thousands of times before it flew close enough to see the wrinkles. The grand finale was not a stunt at the end of a mission. It was the harvest of everything the mission had built, gathered in the only window when the harvest was reachable, in the moments before the machine that gathered it fell silent for good. And the numbers it sent were still climbing outward through the dark, unaware that their source was already gone. Consider what those numbers carried. In the final dive, 8 of Cassini's 12 science instruments were awake and listening. Chief among them was the ion and neutral mass spectrometer, an instrument built to weigh single molecules. For the whole descent it faced directly into the oncoming flow of gas. It was not sampling a moon's thin exhaust this time. It was tasting Saturn itself. For the first time, a machine reached into the upper air of the giant planet and reported what that air was made of, molecule by molecule, while it was still moving through it. No probe had ever done this at Saturn. No probe is scheduled to do it again. Around that instrument, the others worked their own accounts. The magnetospheric sensors read the charged particles in the last thin plasma. The plasma instruments counted what surrounded the falling craft. The radio science hardware turned the spacecraft's own signal into a measuring tool, letting engineers reconstruct the density of the atmosphere from the way the transmission bent and strained. Together they made the deepest direct measurements ever taken of Saturn's outer world. They read the plasma density closer to the planet than any craft had gone. They mapped the magnetic field from inside its innermost reach. They logged temperature and composition where every earlier estimate had been a guess from a distance. And all of it flowed back toward Earth in near real time, second by second, until the antenna could no longer hold its aim. This was the reason for everything else. It was why no cameras ran during the plunge. It was why the thrusters were told to fight rather than surrender. A picture would have been a memory. These measurements were a first and a last at once. The mission chose to spend its final minutes learning something no one had ever recorded. Instead of taking a portrait it could never send home in full, the narrowness of the data channel forced a choice between seeing and knowing. Cassini was built to know. So the harvest of the grand finale was not one number, but a shelf of them. Some had already come from the 22 dives through the gap. In those passes, the spacecraft flew close enough to weigh the planet with new precision. The gravity readings, gathered orbit by orbit, pointed to something strange at the center of Saturn. The core was not the hard, compact ball an older model imagined. It appeared diffuse and blurred, a fuzzy region where heavy elements mix into the surrounding hydrogen rather than sitting apart from it. Inside that smeared heart lay something like 12 to 20 Earth masses of rock and ice and metal, spread instead of stacked. The same measurements sharpened the planet's deep rotation to about 10 hours and 33 minutes, a figure the cloud tops alone could never settle, because the visible bands drift and lie. The magnetometer told a stranger story. Trailing close above the cloud tops, near 2,500 kilometers up, it found a magnetic field almost impossibly clean. Saturn's field is nearly perfectly aligned with its spin, tilted by an amount so small the instruments struggled to see it at all. That should not happen. The rules by which planets generate magnetism usually demand a tilt, a field that neat hints at layers and mechanisms not yet understood, and the close passes even suggested a second shallow dynamo working nearer the surface than the main one. Cassini did not answer that puzzle. It delivered it, fully formed, into the hands of the people who will. There was more in the harvest. The finale confirmed that Saturn's rings are not a fixed and separate ornament, they are falling in. Material rains from the rings into the atmosphere below, as much as 10 tons every second, a steady drizzle of water and methane and other organic compounds pouring down into the planet's upper air. The rings feed the world they circle, and by that measure they are being slowly spent. The close orbits found a previously unknown belt of radiation, created where cosmic rays strike the ring particles. They traced electric currents running between the planet and its rings, a quiet circuit no one had measured before. Each of these was a discovery that only the last approach could reach, because only the last approach dared to fly there. And this returns us to the hardest question the mission ever faced. Not how to end Cassini, but why to end it at all. The spacecraft was still working, its instruments were sound, its long baffled patience had not run out. What had run out was fuel. When the propellant was gone, the craft would drift, unsteerable, still falling along whatever path momentum handed it. That was the danger, not to Cassini, but to what Cassini had found. Because in its years at Saturn, the mission had changed the map of where life might be. It watched plumes of water vapor and ice erupt from the south of the small moon Enceladus, and it flew through them, and it learned that beneath that frozen shell lies a global ocean of liquid salt water. It studied Titan and found a world of rivers and seas and thick organic chemistry, the richest laboratory of complex molecules in the outer solar system. These were the two places a future search for life might begin, and a dead spacecraft, tumbling for decades or centuries with earthly microbes possibly still clinging to it, could one day strike one of them. The chance was small. It was not zero. Planetary protection does not accept a chance that is merely small when the prize is a possibly living ocean. There is a quiet irony folded into that decision. When Cassini first arrived, it carried a lander built by Europe, the Huygens probe, and in January of 2005 it dropped that lander onto Titan. Huygens touched the surface freely, the first landing ever made on a moon in the outer solar system, and no one held it back for fear of contamination. At the time, no one knew that Titan and Enceladus might harbour conditions for life. It was Cassini's own discoveries that raised the stakes. The mission uncovered the ocean and the organics that made these moons precious, and in doing so, it wrote the rule that would eventually require its own destruction. The spacecraft doomed itself by succeeding, so the ending was chosen carefully and early. Steer the craft into Saturn while it still answered its controls. Burn it away completely in an atmosphere that no life could ride out. Turn the disposal into the finest science the mission ever gathered. The plunge was not a defeat handed to Cassini. It was an assignment. The safest place to put a spacecraft that had learned too much about its neighbours was inside the planet none of those neighbours could be harmed by. That is the frame around the final morning. The roll to point the mass spectrometer forward. The thrusters climbing from 1/10 of their strength to all of it. The 91 seconds of held transmission. The 8 seconds of slow tipping, the bare carrier tone, the 24 seconds of a signal with nothing left to say. Every one of those moments was a controlled act, planned years before it happened, by people who had decided that the kindest and most useful death for their machine was to spend it as an instrument to the very last. And when the last of the signal reached Canberra and the loss was confirmed, the room in California already knew what it meant. Earl Mays, the program manager, had described this moment before it came. He had called the final signal an echo, something that would radiate across the solar system for nearly an hour and a half after Cassini itself was gone. Now, the echo had finished. He spoke into the loop of headsets that tied the mission together and said that the Cassini mission had ended that morning, high over the clouds of Saturn, and that the spacecraft was gone. He thanked it. He called it a faithful explorer and bid it farewell. Then he said that the project manager was off the net, and he took his headset off. More than 1,500 people had gathered at the laboratory to be there for it. Scientists who had spent careers on this one machine. Engineers who had nursed it through faults and course corrections across billions of miles. Families who had grown up beside the mission. When the signal ended, they applauded. And then they held one another, because the thing they were grieving had been dead for 83 minutes, and had felt entirely alive on their screens until seconds earlier. That is the peculiar arithmetic of distance. The applause in that room was for an event that had already finished before any of them woke that morning. The light of it was only now arriving. It is worth staying with that gap a moment longer, because it is the strangest true thing about the whole account. Saturn sat about 1.5 billion kilometers away. A signal crossing that distance needs roughly 83 minutes. So the entire final drama, the entry and the fight, and the tipping and the silence, unfolded and was over, while Earth still received the calm, steady voice of a craft in one piece. The people watching the numbers climb were watching a message from a spacecraft that no longer existed. Every reading of atmospheric density, every last molecule counted by the mass spectrometer, was the report of a ghost, faithfully filed, still travelling, arriving on schedule long after there was anything left to send it. None of the instruments knew this. The mass spectrometer kept tasting the gas until the antenna swung away. The thrusters kept firing until they could not win. The radio kept carrying its tone into the dark for 24 seconds after the data stopped. A plain, unmodulated note with no more information in it. The last physical trace of a machine already becoming part of the planet it had studied for 13 years. And that note too took its 83 minutes to cross the distance, so that even the silence had to travel before anyone could hear it fall. There is a reason the spacecraft was sent to burn rather than left to drift. Cassini had spent 13 years finding places worth protecting. Beneath the ice of Enceladus, it found a global ocean of liquid water. That ocean vents into space through cracks near the moon's south pole. On Titan, it found rivers and rain and a deep carbon chemistry. These were the most promising places for life in the outer solar system. And Cassini had discovered them itself. That discovery became the reason it could not survive. A spacecraft out of fuel cannot be steered forever. Left in orbit, it might one day have fallen onto Enceladus or Titan. It might have carried a stray microbe from Earth to an ocean that had never known one. The rules of planetary protection do not permit that risk. So the mission that revealed those worlds was required to leave them clean. There is a quiet irony in the timing. When the Huygens probe landed on Titan in early 2005, no such rule applied. At that moment, no one knew how promising Titan might be. It was Cassini's own work that raised the stakes. The evidence it gathered wrote the sentence it would later carry out. To keep those oceans untouched, the explorer had to become part of Saturn. So the plunge was not an ending forced by failure. It was a choice made years in advance. It spent the spacecraft on one last stretch of science. 8 of its instruments were still awake as it fell. The mass spectrometer tasted Saturn's upper air directly, something no instrument had done. For the first time, a machine measured the planet from inside its own atmosphere. The findings reached deep. In its final orbits, Cassini learned that Saturn's rings are slowly falling into the planet. Close to 10 tons of material rains inward every second. Its magnetometer found a magnetic field almost perfectly aligned with the planet's axis. Its gravity readings pointed to a core that is not a hard sphere. It is instead a vast diffuse region, heavy with rock and ice. It even measured how fast the true interior turns, a question left open for decades. There was more. It found a new belt of radiation trapped close to the planet, made when cosmic rays strike the rings. It traced faint electric currents linking Saturn to the rings above it, and the shape of the deep field hinted at a second, shallower dynamo stirring beneath the surface. These were not the readings of a spacecraft dying. They were the readings of a spacecraft working to the last possible second. Its most productive descent lasted only minutes. The machine that ended this way had been traveling since the autumn of 1997. It reached Saturn in the summer of 2004, the first craft ever to orbit the planet. For 13 years it had circled through the system, past moons and storms and rings. The plunge closed a journey that had lasted almost 20 years from launch. When the signal ended on Earth, the room at Mission Control already knew what the screens could not admit. The spacecraft they were watching had been gone for more than an hour. The program manager spoke a few plain words into the quiet. He said the mission had ended, high over the clouds of Saturn, and that the spacecraft was gone. He thanked it and called it a faithful explorer. Then he took himself off the net and set down his headset. More than 1,000 people who had built and flown it stood and held one another. Nothing about the sky over Saturn changed in that moment. Cassini was already part of the planet. Its metal was scattered as vapor through the winds it had come to measure. What remained was only the traveling report, still climbing toward Earth, still arriving in order. The instruments had done their work in the dark and handed it forward. They had no way of knowing whether it would ever be received. That is the strange gift of distance. It lets a machine outlive itself by exactly the time its voice needs to reach us. For a little over an hour, Cassini was both gone and speaking. It arrived faithfully, reading by reading, long after the hand that sent it was still. The last of what it learned was carried by the same radio that had carried the first 20 years after it left the Earth. And when that final tone thinned into nothing, the great dish heard only the ordinary hiss of the universe. The sky above Saturn had already closed over the place where the explorer had been.